Hello guys, welcome to Aramita Solutions. Welcome to another lesson on physical sciences. We haven't had a lesson on physical sciences in a very long time. So today, let us just come back to physical sciences. We're going to do grade 12 physical sciences. So we're dealing with vertical projectile motion in one dimensions. And we will be looking at graphs. Remember here you plot in this topic you plot the graphs that we talk about. You plot velocity versus time. You plot position versus time. You also plot acceleration versus time. Alright, you also plot acceleration versus time. Right, so these are the graphs that we are going to look at. However, today we're going to focus on this one here. Now, let me remind you of your equations of motion, the equations that you use in this topic. You say final velocity equals initial velocity plus a delta t. You also have one that says final velocity squared equals initial velocity squared plus 2a delta t. Let me do this. No, it'll not work. Let me not. Okay. Okay. I'll try to squeeze them here. So you also have one that says delta. Sorry about that. You also have one that says delta y equals vi delta t plus half a delta t squared. And then you have another one that says delta y equals vf plus vi all over 2 multiplied by delta t. So when we draw our graphs, they somehow are related to these equations. So when I look at this one, if we are drawing position versus time, I see here it has, velocity. It has velocity. So it has velocity as a dependent variable, and it has velocity as, it looks to me like a straight line, as a y-intercept, and this acceleration will somehow look like a gradient, and this will look like your independent variable. So it looks to me this is y equals c plus mx, and this looks like a straight line. This one here, it won't really give me the relationship between velocity and time. So my mistake, this one here is delta y. It's delta y. Okay, so it will not give me the relationship between velocity and time, so let me ignore it for now. Let me come to this one here. It looks like I see it as the highest power of 2. It'll be a parabola, so it looks like a position versus time. And oh boy, it looks like an acceleration, parabola. So I remember a parabola graph had this form. Right? I remember a parabola graph had this form. Right? So now this is the equation that we will be dealing with today. Okay, these are the equations that in fact give us the relationship that we're looking for. Okay, now the relationship of acceleration versus time, because we're using gravitational acceleration, which is a constant. It will always be a constant line, but don't worry, we will get there. So remember I said today we're looking at velocity versus time. Okay, so without any waste of time, let's look at it. So we are looking at velocity versus time graph, right? So today we're looking at velocity versus time graph. So a reminder to you guys, we said they the graphs are coming from this formula, or rather equation, vf equals vi plus a delta t. Remember, these are vector calculations, right? They are vector calculations, so don't be surprised when you find these heads. Okay, now let us now get into details with this topic. So what is happening? We will be having about 4 cases where I will try to help you understand how to draw the graphs, how to interpret them as well. Okay, so without any waste of time, let's look at case 1. So case 1 is a case where an object is dropped. Okay, it is the case where an object is dropped to hit the ground, right? So when an object is dropped, something you should know is that initial velocity is 0 meters per second. Okay, so this means our y-intercept is at 0. So because these are vector calculations, you must choose a positive direction. So let me, on the left hand side, let me choose upwards to be positive. And then on the right hand side, let me choose downwards motion being positive. Okay, let's see how our graphs look like when these directions are chosen. So we had said here, initial velocity is 0. Acceleration, remember, gravitational acceleration is 9.8 meters per second squared downwards. We said downwards, and our positive direction that we chose was that upwards is positive. So since this one is downwards, it will be negative 9.8. In the same way here, initial velocity is 0. Initial velocity is 0. Acceleration, we chose downwards to be positive. Acceleration is positive 9.8. Therefore, the graph looks like this. Vf equals, what is Vi? It is 0. So we can say, this is negative 9.8 delta t. Right? Here, Vf equals positive 9.8 delta t. So this graph is like this, while this one is like that. Now let's draw it. T-axis, V-axis. Okay, with this one, V-axis, T-axis, 0, 0. So this one here, it'll start at 0. It's like this. Okay, and then this one here, again, starts at 0, but remember it's positive, so it's like this. So this is velocity versus time when an object is dropped. So as you can see, y-intercept is at 0. This tells you that initial velocity is 0, right? And this is how your object is. So the final velocity will be the velocity at which the ball hits the ground. So we won't be treating bouncing ball analogy, because I feel like when we treat it, we must use momentum and impulse. So I haven't done a full video on momentum and impulse, so I won't treat bouncing ball analogy as yet. Okay, so in the same way here, initial velocity is 0, but because we had said downwards is positive, when I introduced this equation or this formula, I said your A will represent your gradient. As you can see, your gradient is positive. This is why your graph is like this. Okay, now let us go to case 2. Case 2, we'll say object is thrown downwards. Okay, object is thrown downwards. Okay, object is thrown downwards. So remember, I'm not treating bouncing ball analogy. So here, initial velocity is not equal to 0. Okay, it is not equal to 0. So let's see, positive direction is upwards, and then downwards position is the one that's positive. So let's see. So here, sorry, it is not equal to 0. So here, when upwards is positive, when upwards motion is positive, because the velocity is going downwards, initial velocity, because the object is going downwards, initial velocity must be negative, because downwards is opposite of upwards. So in the same way, acceleration is still negative 9,8 because it's going downwards. It's going downwards. Now here, initial velocity is going downwards because the object is thrown downwards. So it is what? It is in fact greater than 0, which is positive. Acceleration is also going downwards, so it is also greater than 0, it's positive. Now, equation Vf equals Vi minus 9,8 delta t. Here, Vf equals Vi plus 9,8 delta t. Remember, this graph is like this, while this one is like this. Now, with this one, t-axis, v-axis, t-axis, and v-axis 0. Okay, 0. So with this one, we said initial velocity is less than 0. It's negative. So let's say it is here. Your graph will be like this. This one, initial velocity will be positive, so it will be here. Remember, initial velocity is your y-intercept. So this is your initial velocity, right? So final velocity is the velocity where the ball hits the ground, right? It's the velocity where the ball hits the ground. Remember, I'm not treating bouncing ball analogy, right? I'm not treating bouncing ball analogy. So as you can see, this diagram is a bit different to the previous one we did. There, initial velocity was 0. Here, it is not 0. But you must pay special attention to which direction it chose to be positive. Okay? Alright, guys. Now, let's go to case 3. Now, case 3, object is thrown upwards and returns to the initial position. So what is happening here? Here, there's something that is important that we need to mention. The object, when it's thrown up, it must return. So there is what we call time symmetry. Okay, there is what we call time symmetry, which says time taken from point of release to maximum height must be equal to time taken to return from maximum height to point of release. Okay, so time taken to reach maximum height is equal to time taken to return to initial position. Let me highlight this, to initial position from maximum height. Okay, from maximum height. Okay, so this is time symmetry. Okay, now another thing that I also need to mention, at maximum height, Okay, at maximum height, velocity is 0. Okay, at maximum height, velocity is 0. Okay, that is one thing you should know. At maximum height, velocity is 0. Okay, guys. So now, I have mentioned to you that time taken to reach maximum height is equal to time taken to return to initial position from maximum height. On the graph that we're going to plot, you will see this, okay? On the graph that we're going to plot, you will see this. Now remember, here, object was thrown upwards, so initial velocity is not equal to 0, okay? Okay. Initial velocity is not equal to 0, okay? Now, let's show how the graphs look like with different positions chosen to be positive. So again, upwards is positive, and here downwards is positive. Okay, so here we have mentioned that when upwards is positive, what is going on? When upwards is positive, what is going on? Initial velocity here will be greater than 0 because the object is going up. So it's going in the same direction as the positive direction that we chose. So it'll be positive. Acceleration, it is still negative 9.8. It's negative. Now, here, oh, sorry. So here, it'll be negative. So it'll be negative. And then acceleration, obviously, it's positive because we chose downwards motion to be, downwards motion to be positive, right? So obviously we said our graphs look like this, right? So here vf equals vi plus 9,8 delta t, vf equals vi plus, oh man, this is minus, so this is plus 9,8 delta t. So our graphs look like this. This is v-axis, t-axis, origin, t-axis, v-axis, origin. So initial velocity is positive. So let me 1, 2, 3. Let me start it here, and then the graph must end here. 1, 2, 3. The graph must end here. Again here. 1, 2, 3. Graph must end here. So this will be final velocity. This here, let's call it t1. This is time to reach maximum height. This is t2, time to return. t1, t2. So something that I want you to know as well is this. Something that I want you to know as well is this. Is that these arms are equal. Okay, these arms are equal. Remember I said time taken to reach maximum height. Now this point here, velocity is 0. This point here is maximum height. Let me call it h max. Okay guys, let me call it h max. Okay, let me call it h max. Okay, so time taken to reach maximum height, is, what is it? Time taken to reach maximum height is equal to time taken to return to the initial position. So this portion here is equal to this portion here. Okay guys, so here what we call the x-intercept, this is where you get your maximum height. Okay guys, now there's something that I nearly forgot. The area under these graphs can give you the position. So if you were given velocity versus time, and you are asked to calculate the height, the maximum height above point of release, you can simply take the area here, right? You can simply take the area here, right? You can simply take the area here. Okay, you can simply take the area here. The area of this portion here will give you what is this distance from point of release. Now they ask you what is the displacement. To find the displacement, you will say this portion here minus this portion here. Okay, you will say this portion here minus this portion here. That is you finding that is, no, in fact, this portion here minus this portion here. This is your displacement. But if they ask you the total distance covered, it is this portion here plus this portion here. Are you guys hearing me? Remember, displacement is the difference of the positions, but distance is the sum of the positions or distances. So hence I'm saying distance is the sum of this area here and this one here, while displacement would be this one here minus this one here, right? And this will be your displacement. Okay, guys? All right. Now let's go to case. Let's go to case. Oh, I also need to maybe put a short summary here. Something you must see here, something that you must see is that when an object is thrown upwards and returns to initial position, final velocity will be equal to negative of initial velocity. What does that mean? That means final velocity is equal to initial velocity, but in the opposite direction when an object is thrown upwards and returns. Okay, so the velocities are the same. Otherwise, you can say the speeds are the same. Right? So the velocities are the same, but in opposite directions. Okay, remember velocity, speed. There's a video on the differences between the two. Okay, all right, guys. Now let's go to the final case. Now, case 4. Objects thrown. The object is thrown upwards, returns, passes initial position, and hits the ground. Oh my, oh my, oh my. And hits the ground. And hits the ground. So with this one, again, initial velocity is not equal to 0. So without any waste of time, upwards is positive, downwards is positive, okay. Now we are then going to look at it in this way. Upwards is positive, so obviously initial velocity will be greater than 0 because it's going up, but acceleration will always be a downwards motion. Now here it is negative because we chose downwards to be positive. Acceleration will always be downwards, and because we chose downwards to be positive, here the vector will be positive, right? Now VF equals VI minus 9,8 delta T. By now you have gotten a grip of this. VF equals VI plus 9,8 delta T. It's like this. Now check this one out. V-axis, T-axis, v-axis, t-axis. Oh no, this one, let me not do it like this. It must be something like this. T, v-axis. So initial velocity is 0. Right, initial velocity, no, it's not 0, sorry, initial velocity is positive. So let's see. I did that deliberately. So this is initial velocity. Now this is time to reach maximum height, and let me see, this one here is time to return to initial position. This one here is time to hit the ground. Okay, so I forgot my 0. So this is initial velocity, this is time to reach maximum height, and this one here is time to return to initial position, and this one here is time to hit the ground. As you can see now, on the part where the object is moving downwards, that arm is longer. Alright, as you can see here, the part where the object is moving downwards is longer than the part where the object is moving upwards. Can you guys see that? This is the difference with the previous one. Remember, with the previous one, they were equal, but this one, they are not equal. Where the object is returning, the arm is longer, right? Remember, the x-intercept of velocity versus time is the time taken to reach maximum height. Okay, so this is the time taken to reach maximum height, where you find your maximum height. Okay, guys, so with that being said, stay tuned for with that being said, this is all that we can say regarding velocity versus time. Stay tuned for position versus time. Okay, see you next time. Bye bye.